Hi everyone, in this lecture we will talk about combinatorics and we will discuss two important concepts. One is called as permutation and second is called as combination. Okay, so what is this study of combinatorics? It's all about finding the number of ways of choosing some objects out of a collection or the number of ways of arrangement. Okay, so the number of ways of arrangement is also called as the number of permutations. Okay, and the number of ways of choosing an object from a collection is also known as combination. Okay, in how many ways you can combine, in how many ways you can pick k objects out of a collection. Okay, so let us take a real example. Suppose there are 5 members in a club and you want to pick, let's say, one of them as a captain of the club. Okay, so maybe if you have A, B, C, D and E, there are 5 members and you want to pick one of them. So what you can say is either A would become the captain, or B would become the captain, or C, or D, or E. Okay, so clearly there are 5 ways. So mathematically it is also denoted using a symbol which is known as C. So we can say there are 5C1 ways. We want to choose one object out of 5 ways, so there are 5 ways. Okay, so what is 5C1? So 5C1 is denoted as 5 factorial divided by 5 minus 1 factorial, that is 4 factorial, divided by 1 factorial. Okay, so basically it's a general formula of NCR. So NCR is nothing but n factorial divided by n minus r factorial and r factorial. Okay, so this is going to be nothing but 5 factorial divided by 4 factorial, and this is nothing but 5. So this is another way of figuring out how many ways we can choose one person out of 5 people. Okay, so C is known as binomial coefficient. Okay, so NCR is known as binomial coefficient. So very soon we will learn about binomial coefficients and how do we compute them. Okay, but suppose the question is little different. Suppose I want to choose two persons out of 5. Okay, out of 5, then how we can do it? Again, it's going to be pretty easy. So we can simply say it's going to be 5C2. Okay, so I can say 5 factorial divided by 3 factorial and 2 factorial. So it is nothing but 4 into 5 upon 2, which is like 10 ways. Okay, so the number of ways of choosing two persons out of 5 is denoted using 5C2. Similarly, 3 persons would be 5C3, 4 persons would be 5C4, and 5 persons would be 5C5. Okay, so 5C5 would be nothing but 1. So if you want to pick all the persons, it would be 5 factorial divided by 0 factorial, that is 1, divided by 5 factorial. Okay, so it is nothing but 1, and this makes sense as well. Okay, so right now we were till this point, we wanted to choose k persons out of n persons. Okay, or we wanted to choose r persons out of n persons. Okay, but suppose there is a change in the question. Now we want to choose 2 people out of 5 people, but the first person should be chosen for the position of captain, and second should be like vice captain or vice coordinator. Okay, now what can happen is, if you have 5 persons A, B, C, D and E, you can say, okay, earlier I choose A in one of the ways, and now I can choose one of these. Okay, I can choose one of these as a co-coordinator. So with A I have 4 ways, or B could be the captain and one of the remaining 4 could be co-captain. Okay, so there could be another captain that can be chosen in 4 ways, or C becomes the captain, one of the remaining 4 becomes a co-captain, so there are 4 ways. Okay, or D becomes the captain, one becomes the co-captain, so there are 4 ways. E becomes the captain and someone else becomes a co-captain. Okay, so if you add all of these terms, it is nothing but 4 into 5, so it becomes 20. So in this case the number of ways is 20. Okay, so what we are saying is we chose 2. So earlier we had A comma B, choosing these two as one way, but now in this case with B as the captain, A can also become a co-captain. Okay, so what we are doing, we are we are doing two things. We are picking we are picking k persons, or we are picking r number of persons, but we are also arranging them. Okay, so AB is not same as BA. Okay, so A comma B means it is the captain, he is the co-captain. Okay, he is the captain and B is the co-captain. So we are also permuting them. Okay, we are also finding all possible arrangements of them. So in this case, what we will do, we will say, okay, we will first pick our objects, okay, and then we will arrange them. Okay, so picking is same as finding the binomial coefficient. So we can say, okay, out of 5 objects we pick 2, but these 2 objects can be arranged in any order. Okay, so A comma B or B comma A. Okay, so in how many ways we can arrange them, that is nothing but 2 factorial. So if you have R objects, you can arrange them into R factorial ways. Okay, so you will actually do a multiplication here, so into 2 factorial. This is nothing but 5 factorial divided by 5 minus 2 factorial and 2 factorial here multiplied with 2 factorial. So this goes off, it effectively becomes nothing but 5 factorial upon 3 factorial. This is nothing but 5 factorial upon 3 factorial, which is 4 into 5, that is nothing but 20. So you can see this formula is same as the result that we just saw by drawing the example, and we draw the all possible cases. Okay, so in this case what we essentially computed is known as a permutation. So permutation is nothing but it is derived from combination by multiplying with the number of ways, that is r factorial. So it is nothing but n minus r factorial, n factorial divided by n minus r factorial into r factorial. So this r factorial goes off, and hence the formula for computing the permutation is nothing but n factorial divided by n minus r factorial. This term we have multiplied because there are arrangements. Okay, we can arrange the items in these many orders after selecting them. Okay, so I hope you understood what is the permutation. So permutation is a way of choosing r distinct objects out of a collection of n objects, and it can be calculated using the following formula. So this is the formula for NPR. Okay, this is what the permutation is. What is the another thing that we can do? The another thing is known as combination. So combination is the okay, so it's permutation is a way of arranging. Okay, it's a way of arranging r distinct objects out of a collection of n objects. Okay, and combination is a way of choosing r distinct objects out of a collection of n objects, and this is what the formula is. Okay, NCR is nothing but n factorial divided by n minus r factorial into r factorial in the bottom. Okay, so here we do not talk about arrangement, we are just talking about how do we pick those particular items. So that's a brief intro about permutation and combination. Later on we will also talk about binomial coefficients. Okay, so binomial coefficient is denoted using NCR. For example, if you just want to choose 3 cats out of 5 cats, so what you will do, you will say, okay, I will compute 5 C3, n is 5, the number of objects you want to pick is 3, so these can be picked in these many ways. So that is nothing but 5 factorial upon 3 factorial into 2 factorial. So this is going to be nothing but 4 into 5 by 2. This is like there are 10 ways of choosing these cats out of 5 cats. Okay, so there is one shortcut to write NCR. So what you will do, you will write 5. Okay, if you want to compute on pen and paper. And what is this 3? So what you will do, you will write 3 terms in the numerator starting from 5 in the decreasing order. So it is nothing but 5 into 4 into 3, and in the denominator you will write 3 terms in the increasing order, that is 1 into 2 into 3. So this cancels off. This is nothing but again 10. Okay, so this is again one way of writing. So suppose you want to compute 62. So what you will do, you will write two terms in the numerator starting from the 6 in the decreasing order, it becomes 5, and you will write two terms in the denominator starting from the increasing order, starting from 1, so it becomes this is nothing but 15. Okay, so this is where this thing comes into picture. Let us also talk about some basic rules about finding some basic rules which come very handy when we talk about combinations. Okay, so the first one is called as the product rule. The product rule says if there are x number of ways to choose an element A, and there are y number of ways to choose one element from set B. So basically, let's say there are two collection of elements. Let's say we have 5 boys and they are in set A, and we have, let's say, 7 girls which are in set B. So if you want to choose some number of boys and some number of girls, then we will use the rule of product. Okay, so this will be used when there is and. Okay, suppose I say, okay, choose 3 boys and 2 girls. Okay, so what you will be doing, you will say, okay, I can pick 3 boys in 5C3 ways, and okay, and I have to pick 2 girls, so those girls can be picked in 7C2 ways. Okay, so here you will see there is a multiplication because we want both the answer from the left and both the answer from set right, that is the set B. Okay, so let's say you choose some boys, the boy's name is, let's say, A, B and X. If you choose this A, B and X, and if you choose some girls M and N, so these girls can combine with these also. Okay, or there are some other girls, let's say PQ, they can also combine with these. Okay, so that's why with every set of boys you can have every set of girls that is picked. So that is why there is multiplication. Okay, the rule of sum, let's talk about the rule of sum. The rule of sum states if x number of ways are there to choose one element from set A, okay, and y number of is the ways to choose some element from set B, there will be x plus y number of ways to choose one element that can belong to either set A or B. Okay, so if the question is choose either 3 boys or 2 girls. Okay, so if the question is choose 3 boys or 2 girls, in how many ways you can pick? So if you want to pick 3 boys, they can be picked in 5C3 ways, or the option is you can ignore all the boys, you can just pick 2 girls, so that would add the number of ways would be 7C2. Okay, so this is the sum rule basically. Okay, sum rule is or, the product rule is and. So I hope you are getting the basics of product and the sum rule, and that's all for introduction to combinatorics. In the next video we will see how to work with binomial coefficients. Hi everyone, so in this lecture we are going to talk about binomial coefficients and how do we compute the value of a binomial coefficient. Okay, that's what we are going to look at. So one property of binomial coefficients before we begin is they are kind of symmetric. Okay, so for example, let's say if we compute binomial coefficients for 3, okay, so we have n equal to 3, the value of r is going to vary from 0 to 3. Okay, let's say r is 0, 1, 2 and 3, and n is 3. So we have 3C0, we have 3C1, we have 3C2, we have 3C3. 3C0 is going to be 1, 3C1 is going to be 3, 3C2 is going to be 3, and 3C3 is going to be 1. So what you will see is that these values are symmetric about the middle. Okay, so whatever you values have here, you will have the same values on this side as well. So this is because of the fact that NCR is same as NCN minus R. Okay, why this is true, let me tell you. So if you write what is NCR, so NCR is nothing but n factorial divided by r factorial and divided by n minus r factorial. Okay, and what is NCN minus r? So it is n factorial divided by n minus r factorial divided by n minus r factorial. So n minus plus r factorial. So this goes off. Now if you look carefully, this is nothing but r factorial. Okay, this is r factorial, and if you look carefully, these two are same. Okay, these two are same. So that means these binomial coefficients are symmetric. Okay, that is one thing. So we can say ncr is same as ncn minus r. Okay, so if you want to compute a particular binomial coefficient, okay, then one method is the factorial method. You can simply compute n factorial. So this denotes nck. Okay, so you can compute n factorial divided by k factorial and n minus k factorial. Okay, or if you want to reduce it, okay, if you want to make it little easy, so one formula we saw. Okay, one formula we saw. So now this n factorial can be written as n minus k factorial multiplied by some terms from n minus k plus 1 into n minus k plus 2 up to n. Okay, divided by k factorial. Okay, so effectively what is going to happen, this n minus k factorial will get cancelled. Okay, this will get cancelled, and in the numerator you are multiplying these terms. Okay, and in the denominator you are expanding k factorial. So this will reduce the work of your calculation because we are removing the common part. So if I give you an example of, let's say, 5c3, so you write it as 5 factorial divided by 3 factorial and 2 factorial. So what I'm saying is, you can write 5 factorial as 3 factorial multiplied with 4 and 5 divided by 3 factorial into 2 factorial. So this goes off. So effectively you are left with 5 into 4 upon 2, which is 10. Okay, so that simplifies your work. Okay, an easier way of looking at this is, if you want to directly look at, so what you can say, I will have so this is same as writing 5c2, because nck is same as n minus k. We can reduce this to n minus k if the term is getting smaller. Okay, in that case you can say, okay, I will write the first two terms. Okay, I will write the terms in the decreasing order, but only two terms, and I will write the terms in increasing order, only two terms. Okay, so 5 into 4 divided by 1 into 2, so decreasing order, and this is increasing order. So directly you can get this expression, which is now 10. Okay, so this is one way of computing binomial coefficients, and it takes linear time. Okay, it takes linear time in the worst case that we have seen. Okay, then there is something which is known as Pascal's triangle. We also should learn about this one. So here we have a table. Okay, in this table, this denotes what? This is a table of binomial coefficients. In the row we have the value of n, and along the columns we have the value of r. Okay, so if you are in this particular row, in the fifth row and in the second column, then this denotes 5c2. Okay, this denotes 5c3. Okay, now the question is, how do we compute this table? Okay, how do we build this table in a bottom up manner? Okay, how do we fill this table? Okay, so suppose you want to use binomial coefficients again and again, and you want to use multiple such coefficients. Okay, so in that case what you can do, you can use this table based approach, and you can, once the table is constructed, you can query this table. Okay, you can query that, okay, table of I comma j is going to give you the value of the binomial coefficient ICJ. Okay, this is going to give you ICJ. We need to understand how this table is computed. Okay, how this table is computed. So 0c0 is 1, 1c0 is 1, 1c1 is also 1, 2c0 is 1, 2c2 is also 1. So one observation is the first and the last element. Okay, so nc0 is always same as ncn, and it is 1. The number of ways to pick 0 items from n items is 1. The number of ways to pick all items from n items is also 1. Okay, so that's why you will see on the corners the result is 1. Okay, but for these terms like this, okay, what you can observe is that this term is actually can be expressed as sum of two terms. Okay, so there is a recurrence. Okay, there is a recurrence which can be used to define NCR. So NCR is nothing but, let's say this is the nth row and the rth column. So this is sum of cell in the previous row, okay, and in the same column. So that is n minus 1 CR. Okay, so this column is n minus 1 CR plus the column to the left of it. Okay, that is this one. Okay, so plus n minus 1 CR minus 1. Okay, so if you look carefully, this 1 plus 1 is 2. Similarly, for this 3, it is nothing but this 2 plus 1. Okay, this 3 is nothing but this 2 plus 1. Okay, what about this 6? This is nothing but this 3 plus 3. What about this 4? This is 1 plus 3, 4. What about this 5? This is 1 plus 4, 5. What about this 10? 6 plus 4, 10. What is this 10? 6 plus 4, which is 10. What about this 5? 4 plus 1, which is 5. What about this 1? It is the last element, it is going to be 1. Okay. So what about this 6? Sum of these two. What about 15? Sum of these two. What about 20? Sum of these two. What about 15? Sum of these two. Okay. So what you can say is, in any cell, if this cell is n comma r, it is sum of this particular cell which is in the previous row and the column to the left of it. Okay, n minus 1 and r minus 1. So if you add the value here, add the value here, you will get the value at this particular point. Okay, so that means by spending n into r time, okay, we can get the binomial coefficients for all values of n and r which are given in the question. Alright, so once this table is made, a query can be done in just order 1 time. So depending upon the problem statement, you might be using Pascal's triangle, okay, or you might be doing a direct computation, okay. And this is another way of looking at Pascal's triangles. So instead of arranging the values in the form of a table, they have been arranged in the form of a grid so that you can understand. So the corner elements are always 1. So this 2 is nothing but 1 plus 1, 2. This 3 is nothing but 1 plus 2, 3. 1 plus 3, 4. Oh, sorry, 2 plus 1, 3. 3 plus 3, 6. And 1 plus 3, 4. And another thing you can observe is that this is symmetric about the middle. Okay, so 4C0 is 1. 4C1 is 4. 4C2 is 6. 4C3 is 4. And 4C4 is again 1. So this is what it denotes. Okay. Similarly, this is for 5C0 to 5C5. Okay. This is for 6C0 to 65 or 66. 5C5. Okay. So on. This is just another way of looking at Pascal's triangle. So I hope you understood both the approaches. And in the next lecture, we will do a bottom-up implementation for finding the binomial coefficients. And that's all for this lecture. Hi everyone. In this lecture, we'll be discussing the implementation of binomial coefficient. And the approach that we are going to take is a bottom-up approach because the factorial approach is pretty straightforward. So one more thing we need to observe is when we are computing binomial coefficients. Okay, for example, let's say we want to compute the binomial coefficient 5C2. So we discussed that NCR can be written as n minus 1 CR minus 1 plus n minus 1 CR. Okay, so this can be written as 4C1 and sum of 4C2. Okay, so now this 4C1 can be further broken down as, let's say, 3C0 and 3C1, and this can be further broken down as 3C1 and 3C2, and so on. Okay, so this will form a base case. This is kind of a base case. So although you can have a recursive relation, okay, although we can have a recursive relation, but one thing to note is that there are going to be overlapping subproblems. So this can be written as 2C0 plus 2C1. This can be written as 2C0 and 2C1. Okay, so what you can say is this is also 2C1 plus 2C2 and so on. So what you can see is that these problems, they are overlapping in nature. Okay, if we use a recurrence to directly compute this, then it would be inefficient because there are overlapping subproblems. We are computing the answers for same values of n and r, again and again. So this is why we are going to do a bottom up approach. So we are going to make a table of n versus r, and we are going to fill this table. We are going to fill this table row by row, and the first column and the last column for a given value or given row would be 1. For example, this would be 1 1, this would be 1 2 1, and so on. Okay, so let's see how we can fill this table. Okay, so first of all, I will create a array. So in this array, or a vector you can say, so let me tell you. So I'm going to create a vector of int, or let's say it's a 2D vector of vector int, and let's call it as table. So it is going to have, let's say, n number of rows, or n plus 1 rows, and each column, each row would be initialized with a vector with, so each row is a vector with k plus 1 columns, and the initial value is 0. Okay, that's what we do. Now once we are done with this, what we can say is we can simply fill this in a bottom up manner. So I can say for int I equal to 0, I less than equal to n. Okay, I plus plus, we are starting from the 0th row till the nth row, so that's why we need n plus 1 rows, and we are starting from the 0th column and we are going till the rth column. So for int j equal to 0, j less than what, minimum of I and what, k. Okay, and we can say j plus plus. So now we are computing what, we are computing, let's say in the question it is given that, okay, you just want to create till 5c3. Suppose you want to compute 5c3, so you do not need to go beyond the third column. Okay, or if it is not given, if the value of k is not known, then you will take k till the nth column. Okay, so in that case, so we are setting, okay, if the requirement is only up to a certain value of k, in that case we will compute only till k, otherwise we'll compute till n, or we will compute till I. So where I is the row number, that means we are going to compute the entire row. Okay, so base case, the first and the last column would be 1. So if the value of j is 0, or the value of j is equal to I, that means you're computing ncn. Okay, in that case table of ij would be 1. So that is something that we have to handle. Otherwise we can simply use our recurrence. Okay, so what we are saying, okay, we are filling the ith row. Okay, in the ith row, if this j is 0, then it would be 1, or if j is equal to I, then it would be 1. Okay, in all other cases we are going to say this is sum of this term and this term. So these two terms are already computed because we are going row by row. So I can say table of I and j is nothing but table of I minus 1, j minus 1, plus table of I minus 1 and j. That means we are done. And finally, either you can return the entire table, okay, or you can print it. Okay, you can print it as well. So maybe I can say return table of I and table of n and k. So this is another way. So this is helpful if you want to store all values of n and k. Okay, so this will give us the binomial coefficient. So see out binomial coefficient n and k. Okay, or you can simply return the table and you can query. Okay, you can query for a given value of n. Okay, and maybe I can say int query is equal to 5, while query is minus minus. Okay, I can give a value of n, and for all values of n and n. Okay, so we are computing till n and n. Let me just say vector of vector int table, this is equal to binomial coefficient, and I give n and n. Now for different queries, we can just get the answer in O1 time. We can just get the answer in O1 time. So what we are going to do, we are going to scan for each query the value of k, and we are going to say, okay, let's print the value of nck. So I can just see out table of n and k, okay, and we need to make sure that this value of k should be less than n, okay. So if k is less than equal to n, only then we can query the table, otherwise we can't. So let's build the code. Okay, we have some errors. Yes, we need to change the return type to vector of vector int, and yes, we are done. So what we will do is we'll start a terminal, and the code is binomial coefficient. Let's say we have computing for 5. So we have 5 queries. Let's say 5C0 1, 5C1 5, 5C2 10, 5C3 10, 5C4 5, and yes, we are done. Okay, so that means this table is correct, and if you want, you can also print this entire table and see your output. So I hope you understood the bottom-up approach for computing binomial coefficients, and this sometimes may be helpful if you want to uh, make queries, or you have something like, okay, you want to print ncr modulus something, okay, maybe ncr modulus some big number m. In that case, you can put a modulo here, and that should be okay. Okay, so that's all. See you in the next video. Hi everyone, in this lecture we are going to solve a very interesting puzzle which is known as birthday paradox problem. So let us go through the question. So it says, what should be the minimum number of people present in a hall so that there is at least 50% chance of two people having the same birthday? Okay, so this is what we need to figure it out. Okay, there is at least 50% probability of having two people having the same birthday. Okay, this is chance. Now how we can think of this problem? Again, it's pretty vague. How do we start? But let us try to break it down with the smallest possible input. Okay, so let's say if there are only two persons in the hall. Okay, let's say there is a hall, and if there are only a single person in the hall, okay, then that person can have birthday on any date. Okay, so this person can have birthday on any date. Okay, same birthday basically means the same dates. Okay, assuming 365 days in a year. Okay, so now if I say, okay, we have two people and they should have birthday on the same date. Okay, then what is the chance? Okay, so how many people should we have in the hall so that we can say with 50% confidence that at least two people are going to clash their birthdays? Okay, so now what happens if there is a single person? Okay, if the number of person is 1, then he can choose his birthday on any one of the days. Okay, so he has 365 options to choose his birthday. Okay, and divided by 365 out of total options. So I'm not calculating. It's difficult to calculate for the same birthday because we don't know what two persons will have the same birthday. Okay, it would be a lot of combination. So what we are going to do, we are going to slightly twist this question. So we are going to say, okay, if p denotes the chance that two people, at least two people, have same birthday. Okay, have same birthday. Okay, then can we say 1 minus p denotes the probability that all people have different birthday, have different birthday. Okay, so these two are complementary. Okay, so p denotes the chance at least two people will have same birthday, then 1 minus p will denote the probability that all people will have different birthday. So we can easily compute this. All people have different birthday. How? Let's see. If there is one person in the hall, then there is 100% chance that his birthday will not clash with anyone else. Okay, his or her birthday will not clash with anyone else. So this is one, that is like the 100% probability. Okay, now let us talk about n equal to 2. Okay, talk about n equal to 2. That means if there are two persons in the hall and I want them to have different birthdays, the first person can choose out of 365 days any one day it can choose. Okay, let's say we have 365 days and the person says, okay, my birthday lies on this date. So for the first person has again 365 options out of 365 available options. But for the second person, if the second person wants to have a different birthday, then we can say that the second person should have 364 choices, because this choice is already taken. So the second person will have only 364 choices available. So I can say into 364 upon 365. If you do this multiplication, okay, if you just do this multiplication, let's see what it turns out to be. So I can say, okay, P2 for the second person, it would be 364 divided by 365. And what is P2? It is 99.72. Okay, so this is nothing but 99.72. So that means there is a probability that there is a 99.72% that these two people will have a different birthday. Okay, so if I add one more person here, if I add, let's say, one more person here, person is P3, and let's see what happens now. If this person also joins the hall, then for n equal to 3, it would be what? It would be same 365 divided by 365 into, for the second person it would be 364 upon 365. Now two days are booked. Okay, this is booked by second person. Now the third person wants to have a different birthday, so he is going to choose one of the 363 options. So he can choose his birthday in 363 ways divided by 365. So let's see what this value turns out to be. So what you can do, you can do P2 multiplied with the probability for person 3 would be nothing but P2 into 363 divided by 365. Okay, and what is P3? It is 99.17. okay, so it is 99.17%. So what you can observe is, okay, I will just write it here. Okay, it is 99.17%. So what you can observe is, as the number of people are increasing, okay, as the number of people are increasing in the hall, the probability that they are having different birthday is going to decrease, because as you keep on adding more people, the higher is the probability that they are going to have a same birthday. Okay, the probability of having different birthday is decreasing, and the probability of having same birthday is going to increase, because that is nothing but 1 minus p. Okay, probability of having same birthday is going to shoot up. So what we need to do, we need to compute. Okay, so what we will be doing is, I'm just going to erase this one. So what we will be doing is, let us talk about what we are going to do inside the solution. So we are going to say, okay, we will start with a particular value of n. Okay, let's say n is 1, n is 2, n is 3. We are going to calculate the probability of different birthday. Okay, let's say if this probability is p, then probability of having same birthday, it's going to be what? It's going to be 1 minus p. Okay, so we are going to say, okay, we want to compute when this probability is 50%. Okay, so we can simply say, okay, we will start from certain value of let's say this is 100%, this is 99.72, this is 99.17. okay, we need to see when this value drops just below 50. Okay, so when we say it's just below 50, let us say it is 49.98 or something like that. Okay, this value would be just above 50. Okay, just above 50. So what we will do, we will use a loop, okay, and we will see when this value drops just below 50, then we will get the answer. Okay, for this number of persons in the hall, the probability of having same birthday is just 50% or just higher than that. Okay, so the 50% might not be exact, it could be like 50.1 or 50.02, something of this sort. Then we will stop. Okay, so at least 50% probability we want, and this is the value of p that we will get through this loop. Okay, so I hope you got a high level idea, and what I would suggest is you try to code it on your own, and in the next lecture we will discuss the implementation for the same. Thank you. Hi everyone, so let's code the solution for the birthday paradox problem and find at what values the probability is 50%. Okay, so I will say, okay, the number of people in the hall is initially 1 or 0. Okay, and I can say, okay, in order to compute a probability I need two numbers. One is a numerator value and another is a denominator value, that is also 365. So what we discussed is, as the number of people are increasing, the probability is becoming like this. So 365 upon 365 for person 1, 364 upon 365 for person 2, 363 upon 365 for person 3. So at some person equal to some number of people, it would be like 365 minus the value of people plus 1 upon 365, because this is the general pattern. Okay, so you can see this would be the value of numerator, it is continuously decreasing, the denominator is same. So what I can say is, while let me also write the probability of having different birthday. Okay, that is 0.5. I can say while probability of having different birthday is greater than 0.5, sorry, this is going to be initially 1, because let's say there is one person in the hall. Okay, so what we can do is we can say for the second person, we can start from the second person. Okay, or we can say, we can simply say, let us say, yeah, so this probability of having different birthday will be multiplied with the previous value into the current value. So the current value, if you do it from person 1, it is nothing but 365, that is numerator, divided by denominator, no change in that. But for the next person, the numerator is going to be reduced by a value of 1 and the denominator will not change, and the number of persons in the hall, that is this particular p, okay, at this particular p will change. Okay, this number of people is now going to be 2, so I can say people is going to be people plus 1. And one thing we can do is we can print this probability, so I can say see out the number of people is this much, that is people, and I can say, okay, the probability is this much, that is probability of having different birthday, and so that you can see how this probability is getting reduced. And finally you can say, okay, final answer is what? Final answer is going to be people. Okay, so let me just tell you what is going to happen. So finally, why I have written this probability greater than 0.5, because this probability starts from 1, it dips to like 0.9972, then it dips to 0.9917. Okay, finally it would be like 0.51 something, 50 something, and when this loop will stop it would be 0.49 something. Okay, so when this condition is false, this loop will stop, and for that condition, whatever is the number of people we have, that would be printed. Let me just show it to you. So let's go to the terminal and let's say /birthday paradox, and you can see finally when you have 23 people, the probability is dipping to 0.4927. Okay, so when there are 22 people, that means there is almost a 48% chance of two people having same birthday. But when when there are 23 people, there is 0.4927. That means the probability of two people having same birthday is slightly greater than equal to 50%. Okay, the final value of n should be 23. So that means with 23 people, the probability is at least 50%. Okay, so yeah, let's run this code. Okay, so you can see final answer should be actually 23, not 24. So here we should output people minus 1. Why? Because when this condition is false, so you can see at n equal to 23, we have already violated this condition. Okay, but which is fine, but we are also doing this increment which is not required. Okay, so as soon as this becomes, as soon as probability of different birthday becomes greater than 0.5, okay, oh sorry, less than 0.5, we should break the code. Okay, or maybe you can do something like this: while 1, if probability of different birthday becomes less than 0.5, we should break the code. Okay, that is also fine. You can do this thing as well. And yeah, let me show it to you. Okay, you can see the final answer is 23. The only thing is you're not getting this statement. If you want to print this, you can print it here as well. That's fine. And yeah, so you can see final answer is 23. Now we can remove this particular statement. Okay, and we can simply print the final answer, that is 23. So yes, 23 is the final answer for this particular problem. Now there is one small twist that I'm going to give you as a homework. Okay, so what is the homework? So instead of doing it for 50%, okay, instead of doing it for the 50%, you have to do it for any value of p. Okay, so what is the probability when at least two people have same birthday and their chance is, let's say, 75%. Okay, or their chance is, let's say, 62%. Okay, this you will take as a input from the user and you will accordingly modify the code. Okay, and second is, what happens if I say, okay, I want 100% probability that at least two people should have a same birthday. Okay, this is going to form a special case. It's going to be a special case. So in what case I can say how many people I would need so that there is 100% chance that at least two people will have the same birthday. Okay, if I say, okay, um, if I have 365 buckets, okay, and if I put 366 people inside it in the hall, then at least two people are going to have the same birthday. Okay, so you can have input as if p is equal to 1, then you can say see out 366. Okay, so this is going to be kind of a special case that you should be able to handle. And that's it for this lecture. Okay, hi everyone, so now we are going to discuss a problem that is related with BST and also with dynamic programming. So let's discuss this question. Very interesting problem statement. It says we need to count the number of binary search trees that can be formed using n number of nodes which are numbered from 1 to n. And let us see these two test cases. For example, if n is 3, we get the output as 5, and if n is 4, we get the output as 14. So let us discuss, if I'm given 3 nodes, then how many BSTs I can form. So n equal to 3 means we have 1, 2 and 3 nodes. And if I make BSTs, so if I just put 1 at the root node, then I can get this particular tree 1, 2 and 3, or I can also get 1, 3 and 2. Or if I put 2 as a root node, then only one tree is possible, which is this. Or if I put 3 as a root node, then I can get 1, 3, 1 and 2, and I can also get 3, 2 and 1. So in total we can see there are 5 different type of BSTs that can be made. Now let us discuss how we can solve this problem for any given value of n. Now we have nodes which are numbered from 1 till n, okay, and I want to generalize that if I take the ith node as the root node, then how many trees can be formed? Once I know, okay, with ith node as a root node I can form, let's say, some number of trees, then I can just do the summation for all the nodes. Now what will happen if you put ith node as a root node, and since it is a binary search tree, then all the nodes which are to the left, they will be a part of the left subtree. So in the left subtree we can have I minus 1 nodes, and all the nodes which are here, they will be a part of right subtree. So in the right subtree we will have n minus I nodes. And let us also denote a function f of n that basically tells us how many trees can be formed using n nodes. Okay, number of BSTs that we can form using n nodes. So that is basically what we want to find out. So with I as a root node, we can define a recursive sub problem. Okay, so if this left subtree has I minus 1 nodes, that means in how many ways we can form BSTs in the left part. So let us say that is going to be f of I minus 1 node. That is going to be f of I minus 1. Okay, now let us say this value is going to be x. What is the number of different BSTs that we can form for the right subtree? Since we have n minus I nodes, we can say this value is going to be f of n minus I. Now in order to form this particular BST with ith node as the root node, I have x number of BSTs possible in the left, y number of BSTs possible in the right, and how many BSTs I can form with this ith node as a root node. That will be, I can choose one BST from the left in xe1 ways. I have one way to choose the root node, and I also have yc1 ways to choose one of the BST from the right. So this turns out to be x into y. So for n nodes, what I can do, I can say with ith node as a root node, this answer is going to be nothing but what is x? X is f of I minus 1, and what is y? It is f of n minus I. Okay, and this is going to be summation of f of I minus 1 into f of n minus I for all the nodes starting from 1 as a root node till n as a root node. Okay, so this is the recurrence that we have derived, and we also should know the base case. If we have 0 nodes or if we have 1 node, the answer is going to be 1. So this is the complete recurrence that we have derived, and using this recurrence we can actually find out in how many ways we can construct binary search trees with n nodes. Now let us also see this with the help of one example. Okay, let me show you one example now. Let us say I want to compute number of BSTs for n equal to 3 and for n equal to 2. Okay, so for n equal to 2, let's do it first, because for n equal to 3 we will require the solution to this particular sub problem. So if the value of n is 2, that means we can make either 1 as a root node or we can make 2 as a root node. Okay, so both these options are there. So when the value of I is 1, so what is this value? I is 1, so it will be f of 0 into f of n minus I. N is 2, I is 1, so it will be f of 1, plus when the value of I is 2, so it will be 2 minus 1, that is 1, and 2 minus 2, that is 0. Okay, so you can see this will be 1 into 1 plus 1 into 1. That means 2 BSTs are possible, and which is true because when you make when you have two nodes, either you can make 1 2 or you can make 2 1. Okay, so when you're using 1 as a root node, you have one BST. When you're using 2 as a root node, you also have one such BST. Let us see what happens when n is 3. So when n is 3, you can have either I equal to 1 as root node, I equal to 2 as root node, or I equal to 3 as root node. So when I is 1, this formula becomes 1 minus 1, that is 0, into f of n minus I, that is 3 minus 1, that is 2. So f of 0 is 1 from the base case. F of 2 we have already computed. This is 2. So it becomes 2. This line basically represents when you have I equal to 1 as root node, you get 2 BSTs. And you can see these are the 2 BSTs that we are talking about. And f of 0 is 1. That means for the left part, okay, there is no such node. And for the right part, there are 2 such nodes. And those 2 nodes can be arranged in 2 ways. And the left node, because there are 0 nodes, there can be only one way possible. So it becomes 1 into 2, that is 2. That's fine. When you have I equal to 2, so this becomes 2 minus 1, 1 into 3 minus 2, that is 1. So it is 1 into 1. So that means when you have 2 as a root node, there is only one BST possible, that is this one. So it becomes 1. And when I is 3, that means you are taking 3 as a root node, then it will become I minus 1, that is f of 2 into f of 0. That means f of 2 is 2 into 1. So same case as the first one, but in opposite direction. So you have 2 nodes in the left, you have 0 nodes in the right. So these 2 nodes can be arranged in 2 ways. You can see this structure here. There are 2 ways to arrange these 2 nodes, and we are actually getting this answer from this sub problem that we have already computed. So you can definitely see there are overlapping sub problems here, and that is why we can optimize this using dynamic programming. So if we do this summation, we will get 5 as our answer. So I hope you really understood this concept and how we derived this particular recurrence and solved this particular problem. So that's all for this lecture. In the next video, we will see the implementation. Hi everyone. So let us discuss the recursive and the top-down implementation for Catalan number. So in the recursive case, I can say if n is 0 or n is 1, I can return 1. Otherwise, we can build our answer by iterating over all the nodes. So I can pick all the nodes from 1 to n as the root node. I can count the number of possible ways for the left subtree. That will be count of BST of I minus 1. And I can also count in how many ways I can make right subtrees. So that will be count of BST of n minus I. And finally, my answer is going to be incremented by vector of x into y. And from here, we can say we are going to return the answer. So that's the recursive code. Let's build it. Let us also run it. So for n equal to 3, this answer should be 5. So you can see it is 5. For n equals 5, this should be 42. Let's see. And you can see it's working fine. Now we can also convert this code into a top-down DP code. Let us see how. So we can create a copy of this function, and we need to pass a DP array to memorize the results. And here we can check if DP of n is not computed. So I can say if DP of n is not 0, that means some value is already stored, then we can compute it. Otherwise, if it is already computed, then we return it, and if it is not computed, then we store it. So here and here also we pass the DP array, here also we pass the DP array, and let me call it as top down. And in the main, I need to create a DP array and initialize it with 0, and I can call this function count BST top down with the value of n and the DP array, and let us see the answer now. Okay, so yeah, this call should be top down, this call should also be top down. Okay, let me just make it 100 for now and do it. So you can see in both the approaches the answer is same, but the recursive approach takes exponential time and this approach is going to iterate over n states, and for every state we are doing an order n work. So this actually takes order of n square time. So this one is better, and in the next video we can do the bottom up approach for the same. Hi, so let us discuss the bottom up DP solution for the count BST problem. The idea is we need to fill a DP table in a bottom up manner, starting from n equal to I equal to 2, because for the base case we know DP of 0 and 1 are going to be 1 for all values of I till n. Okay, so let's say this is DP of I. We want to fill this value, and we have already seen that it depends upon the solutions for the sub problems. Like for f of 3 we saw it depends upon f of 0, f of 2, and it also depends upon f of 1, because this was how the recurrence look like. Okay, so for any value of I, it depends upon all values j, such that j is lying in the range 0 to I minus 1. So we will try to define dp of I in terms of dp of j. So let us see how we can code this solution. So what I will do, I will say, okay, dp of 0 is going to be equal to dp of 1, it's going to be 1, and for int I equals to 2, I less than equals n, I need to iterate on smaller sub problems for j equal to 1, j less than equal to I, j plus plus. That means if I am computing dp of I, that means we are storing for, we're computing for a value of n that is equal to I, and let's say n is 5. Okay, so we are iterating, okay, from j equal to 1 till j equal to I, yeah, j less than equal to I. That means we are treating all the nodes as root node. Okay, so this should be actually I, so we should go from 1 till I. Okay, either we go from 0 to I minus 1, or we go from 1 to I, both are fine. Okay, both are fine. So if we make 1 as the root node, then what will happen? If we make 2 as the root node, then what will happen? This is what we are doing. So we can say, okay, dp of I, that is our current answer, it will be incremented by a factor of dp of j minus 1. So if I'm computing for a value of n that is equal to I, so that means if I make this jth node as the root node, then I will have j minus 1 nodes in the left, and I will have I minus j nodes on the right. So this is what I'm doing. So my answer would be the term x. Okay, so this term would be dp of j minus 1 multiplied by dp of I minus j. That's it, and from here we can return dp of n. So that completes the bottom up dp solution. Okay, so in this case this I is behaving like n, and this j is behaving actually like I. So if it is confusing to you, I can also make it a large n, I can make it a small n, and I can say n plus plus, and here I can say this is I, this is less than equal to n, and here I can say dp of I minus 1 into dp of n minus j, and this will be dp of n, and here we can return dp of n. So this is another way of writing the same code. So this would be dp of n minus I. Okay, so this is how you can relate this code with this code. So I just changed the variables so that it looks more familiar to you, and we can now test our code. So let me run it, and you can see for all the three cases we are getting 42 as our answer, which means this code is working perfectly fine. So that's all. Thank you.